I present the joint work between the, where is it? There it is. The University of Mainz, the Computer Science Department, where I am, and the Max Planck Institute for Chemistry. And to introduce and motivate a bit the talk is, I have to talk a bit about emotional response analysis. And that's a field in psychology which basically analyzes the reaction of humans to certain emotional stimuli, which is usually done in experiments, which you have here. People get shown some pictures which are sad or happy or something else, and they measure certain moduli, some brain activity using EEG or skin resistance. Now, what is not that well studied and examined and not known much about it is what we breathe out, basically. So we all know we breathe out CO2 and water, but not only that, we breathe out hundreds of compounds which are all around us at the moment. And what is not really well known is, do we react to certain stimuli like happiness or sadness by breathing out certain molecules, and do we maybe communicate by that? And if we communicate, which molecules do we basically breathe out given certain emotions? And these molecules which you have are called volatile organic compounds, or VOCs. And the good news is they can be measured in the air using these machines, that's mass spectrometers. And they basically measure the concentration of these VOCs in the air. It should be noted that they don't measure actually the concentration of the compounds. You don't know which molecule it is, you only know the mass of the molecule. But anyway, so yeah, and this is the question we focus on. So basically, what do we breathe out given certain emotion reactions? And we thought on which experimental setup is good for that, and we came up with the perfect setup in a cinema, actually. So what you have in cinema is a large number of people sitting in the audience, and they are all sitting there looking at one thing, and namely the movie, and it causes some reactions in their emotions. And it's a closed box, so it's really controlled. They're not distracted, they don't use mobile phones, they don't talk, and they all breathe something out given the movie, given their emotional response to the movie. So yeah, that's what we did. The cinema is connected to a ventilation system that sucks out air from the outside. In the cinema room, there the people breathe something out. The concentration of some VOCs get higher, and that's sucked out of the cinema screening room into the ventilation system again. And there we plugged in our mass spectrometer and basically measured what the people breathe out there. Now, yeah, we found a cinema in Mainz that was nice enough to let us measure that. And we measured that for 4 weeks. And that's kind of the result of that. So this is the concentration of CO2 in that cinema. We measured 4 weeks in December 2013, and we have every 30 seconds one measurement. So we have approximately 89,000 measurements. And we don't only have CO2, this is a nice example, that's why I show it, but we have 400 VOCs measured, so this times 400. And in the total, in the whole 4 weeks, we had a total of approximately 9,000 visitors in the cinema. So it's really a huge experiment, actually. And now, if you look at the data, what you have here, you see these peaks. It goes higher and lower, and it's CO2. So the more people are in the room, the higher the concentration is. So here you have quite a few people in the room. Here you have lower, and you see the times where there's no movie running. We just kept the measurement running the whole time. And so if you look into it more details, so I zoom in into this day, that's 26th of December. And what you see here is basically already the movies. So one movie was running here, another one was here, another one here, and here's part of another one. Here nothing is going on. There was a movie from the previous days. The concentration of CO2 is high, then it goes down because no one is inside, it gets sucked out. This is no movie, that's actually the cleaning staff coming in the room. And you see really nice these movies. And if you look a bit more detail into the one movie, that's the Hunger Games Part 2 running on that day, you see this shape basically. And the shape is pretty typical. We call it shark fin shape because it slowly raises in the beginning, and at the end it quickly goes down. And what happens in the beginning, people come into the movie, not all at once, but over a certain period of time. So the concentration of CO2 goes up slowly, and then it reaches a certain plateau. And at the end, the credit starts, and it quickly goes down. Now, what you also see is that it's really not a plateau. It has peaks, ups and downs. And the question is that somehow related to the movie? And to look into that, that's the same plot, basically, just a bit scaled down. You'll see in a moment. and it's between 12:30 and 5 o'clock. And yeah, this is basically Hunger Games. And if we look at the next day, the same time frame, that's another Hunger Games running, and the next day, and the next day. So you see already that this kind of aligns really well the peaks. So here I marked them. And you see the peaks perfectly align on these. So the concentration raises at the same time every day. And that's not random. It's really related to events in the movie. So if you watch Hunger Games or not, it's basically this period here, there's a tournament to the death. So there are many fights. And we have the movie, so we can look into it. And it's always here some fighting scene. Then a recover scene, so the people relax a bit, don't breathe that much, so less CO2 in the room. Then there's a fight scene again, then relax, fight, and so on. So this really reflects what's going on in the movie. And again, this is CO2. So CO2 reacts on everything. The moment the movie is more action, we breathe more. So we get more CO2 in the room. The movie is more calm, we relax more, and less CO2 in the room. But we don't only have CO2, I said we have 400 measurements. And these other 400 VOCs, they don't react on everything, that they only react on certain things. And there's certain peaks only in certain movies. So the question is, on what? So maybe there's something specific to fear or to happiness or something. And so our next task was to relate that basically to the movies which were showing in the movie, in the cinema, sorry. And that's this. So the next problem is, the problem is there's no, we have the movies, so we can watch the movies, but there's no data set explaining the movies. So there's nothing, minute 5 is action, minute 7 someone is dying or something. So that is really not available for these movies, especially when we started the experiments, they were rather new in Germany. So we had to label the movies ourselves, which is a really hard task and quite annoying actually. In total, we had 50 movies and 104 screenings in these 4 weeks. But as we had to do the labeling ourselves, and I said it's really hard, we just selected these 6 movies for the analysis. And we labeled them by multiple annotators. And in total, then we had 63 screenings of these 6 movies. But due to problems in the measurements of the data, not all were usable, so 46 we could use, 46 screenings. But then we had the next problem. There's no standard scheme for labeling scenes in a movie. So there's some research going on into that, but there's no one who ever came up with a scheme saying action, romance, or whatever. There are some selections which focus on some parts of the, there's a data mining paper a few years old which goes action, explosion, and things like that, but not really something covering the whole spectrum. So again, we had to define our own labeling. So we came up with a labeling system for the scenes, which was a combination of several things. Some papers we assembled from movie analysis, from data mining, and also IMDb categories, genres we use. Not all of them. Documentary is quite unusual, but we have something like romance or action, which we could map to the scenes, basically. Yeah, so we did that with these labels. We have approximately 45 labels, and we did that by multiple annotators. In this paper, we used 3 annotators, and they annotated the movies, and then we averaged the annotation over them. So 2/3 of the annotators had to agree on a label. These movies we selected, partly these 4 movies, we had a lot of data on them. And for these 2 movies, Machete Kills and Paranormal Activity, we hoped for a strong reaction in the audience, because many chopped off hands and many shocking moments. Good, so now we have basically 2 data sets. One is the measurements of the VOCs, and the other one is the scene annotations, and then we went on to the analysis. Now the analysis basically is, what we do is kind of predictive time series prediction, but it's only to understand the data. We don't really try to predict something. We want to understand what's going on in the data. And obviously it's time series, so the first thing what you can do is you use the labels from the movies which you have and the concentration of the VOCs in the air, and use a certain time frame. So we took 5 minutes basically, and predict the next concentration of the VOCs in the air. And that's what we call forward prediction, and that kind of works well. We get really good with the evaluation, like high correlations there of 95 or something for many masses. Now, but what's kind of more interesting for us, and what's a really nice step, is something we call backward prediction, and which is a bit not intuitive because we predict the past. So what we do here is, given the input of the next 5 minutes of the concentration of all VOCs, can we basically build a model that predicts what was going on right before that, what scene was showing there? So was an action scene given that what we breathe out? And we evaluated also that works also really well. We get high area on the rock curve, so there's definitely some signal in the data. And another thing what we did is, as we have these two steps, we can basically do something we call forward-backward, which is we go a certain time frame in the future, fill the data with the predictions, and then use the backward prediction to go back and evaluate basically our predictions. Now, as this is kind of the most interesting part for us because it gives us the relations between the labels and the masses, we did some more analysis there. So we tried, so this is the same figure basically, and we tried to extract basically some causalities in that data. And we used a method which is kind of close to Granger causality. So if you think about it, we can do this and we can evaluate that. So we get a rock curve, we get an area on the rock curve, we get a result for that. And then we can do the same again, but we leave out all the measurements of CO2, let's say, and then we get another rock curve and we get a difference between these rock curves. And if that difference is high enough, if it's significant and a low p-value, then we say this is really important because we need the CO2 to predict this really well. And we did this for the next one, and if the difference is not that high, it's not that important, so it's no causal relation maybe there. And if it's high enough, like this one again, then you have hints for a causal relation there. Yeah, and that's it. And for the results then, so we did several evaluations. One was 30% holdout, so we left out 30% of all screenings and used that in the test set. And that works quite well. We have really high, as I said, we have high correlation coefficient for the one prediction and high AUCs for the backward prediction. Then we did something called leave movie out, basically. So we left out single movies and tried to predict from all movies, but that one, all screenings of the other one. And that doesn't work well because we have really distinct sets of labels. They are not very similar, so we don't have really big test and trainings. But still, some labels we could predict really well. And the interesting thing, which we are also at the moment really looking into, is the causal relations which we try to identify there. And we found some things which at the moment the Max Planck Institute is actually looking into it. One thing is between blood in relation to violence, so really with fights and not cutting yourself in the kitchen. We found a causal relation to ammonia. Now, ammonia is, in urine, but that's hopefully not the reason for that. But it's also in sweat, so that kind of makes sense. So we have, the people see blood on the screen, and they kind of start with sweating, which is, blood and violence, so they're fights, you might be a bit tense, so sweating seems to be a good explanation for that. Another one we found to acetone. Now, acetone is a molecule which gets released by us when we do a lot of sport, but that's not the case there. The people sit still, like you now. And already before we did some preliminary analysis of clustering and whatever, and we identified that acetone, there might be some relation, some signal we send out with acetone there. So that's one of the targets we focus at the moment on and try to understand the metabolism in the body which causes that. Another interesting one is comedy and formaldehyde. Now, formaldehyde you might know from basically biologists use that to preserve their turtles and snakes and whatever. We didn't see that in the cinema, but formaldehyde is also a breath gas. It's known that we breathe it out, and this is actually kind of cool because we found a relation to something which is known that we breathe it out. So this kind of proves our hypothesis that some signals might be transmitted by breathing. Actually, the same with the acetone. It's known that we breathe it out, and it's used in breath analysis if breath is analyzed for detecting certain illnesses. There are some machines for that. Now, as I said, for this paper, we had 3 annotators only because it's a hard task. Later, we hired some more students to do that. First, they were excited, then they found it also boring. And we did more annotations, and we redid the experiments and found really good results for these labels, which is kind of cool because these labels are really something which draws your attention to the movie and causes maybe strong reactions. So it's suspense, injury, hidden threat, mystery, and comedy. And again, we found some more causal relations, hints to causal relations basically there. from suspense and romance to isoprene, and isoprene is a similar story to acetone. It's also released when you move, and it's also, again, we thought before it's maybe something we use as a signal, and it's also used in health analysis of the breath. Yeah. Another one is siloxanes, and that siloxanes is, we don't breathe it out, and we don't produce it, basically. It's in shampoo and cosmetics, and like this, I release siloxane now here. So it doesn't seem to make sense, but we have actually in every movie, we have 2 peaks of siloxane. One in the beginning when the people come and undress their jacket, and one at the end when they dress again. And another thing is we find injury a lot in our movies at the end of the movie. So what we think is that we pick up the signal at the end. When the people see an injury, they don't breathe something out, but they dress and release siloxane in the air. Okay. And with that, if it switches, yeah. Come to conclusions. So the good news for you is actually the data set is freely available. We released it on GitHub. You can download it and analyze it. If you find something, please tell us. We're really interested in that. At the moment, we're identifying these molecules and find the relations there and where they come from. And we have a huge list of actually these causal relations, and we're looking into that. And it's really a hard task because related to the metabolism and so on. Now, another thing we did new experiments in February, which is not part of the data set yet, but this is more with psychologists together. So we measured single people in something like a cell, isolated, and we showed them pictures and measured the air and also their brain activity and skin resistance and muscle movement. And we tried to relate that now with previous psychology experiments. We plan to do new measurements actually in a cinema again at the end of the year, because we think that's really the perfect setup we found, and we want to increase the data set and maybe select also movies which fit better, because we only had these big blockbusters. We also wanted something like erotic, because that might cause more reaction in the audience. Now, we also plan to have new setups. So if you have funny ideas, please tell me. We're thinking really hard on what to do. We thought on pilot tests in these simulators or something. So if you have any ideas, please tell us. We are thinking on new experiments there. And to summarize, what I presented you was really a unique combination between atmospheric chemistry, which measures the air around us, the breath analysis, the molecules we breathe out, emotion response analysis. We also work there with psychologists together, movie analysis, and we use data mining them actually to find relations in that. And with that, I thank you for your attention. If you have any questions.
Thank you. Time for questions.
Thanks. It was a very good talk. I've got one quick question. Do you know what was the volume of the room of the cinema versus the headspace versus the breath that people breathe out?
So yeah, I mean, we have that everything. We don't have it in the paper, but we can get that also from the cinema. But I don't know it actually at the moment. I know it's approximately 400 people can sit in the room. And actually, there's also a delay between the measurement and the people. Yes, it's like it takes 2 minutes from the air from the last person in the room getting to the machine. But the details I don't know by heart, but I can look them up. So yeah, just write me an email. I can find it out. Yeah.
So I guess a very natural question would be to try to find out who's actually in the room. So let's say if it's a chick flick, there's probably a higher chance that there'll be a lot of siloxane being released. And well, depending on the audience, I mean, depending on how old they are, they may have very different metabolism. Do you have that data?
Mm-hmm. So we know we have a lot of data from the cinema itself. We have which tickets are sold, so we have discounts. We know approximately how many kids are inside. We know how many grown-ups. But also, I mean, the day of the time and the kind of movie gives us a bit of a hint there. Yeah. We don't know exactly is that many women, that many men. No, that we don't know. And that's what we try to find out with the other experiments. We have single people. And there, yeah, there's actually a difference between men and women. And also in the reaction, first of all, in the reaction and what we breathe out. So with our experiments, which we had then, there was some erotic inside, which we were interested in scientifically. There you have that women react completely different to men on erotic pictures, actually. So, and you see it by what we breathe out. So women seem to have no reaction men have a really strong reaction, obviously. Yeah. And there are other things where they differ, but this was the strongest signal found. Yeah.
Because you could basically use this to deaggregate.
Yeah, exactly. So that was the goal, but that's why we did new experiments to put that in the data.
I'll leave it there for
Okay.
time, but thank you again.